45, 50 minutes, 60 minutes, depends. So I mentioned earlier that I was motivated to develop PLAF by watching fluid mechanics movies by my computational friends. And so we have to do this too. That did get them interested. But it was only until we started to work on low temperature flows that they really got interested. So that led us to, can we do PLAF with something other than OH? We did OH in the early days, and then nitric oxide. Question was, what are the tracers you can use to do PLAF at room temperature? There's no OH at room temperature. People don't like to use NO, it's toxic. What can we do at room temperature? And that led to the idea of developing some tracers. We started with something called biacetyl, which is a particular molecule that was, I believe, is used in some of the flavoring that's on popcorn that you might have smelled at the theater. So we found that this liquid could be evaporated and give us a vapor, which happened to absorb light at the wavelength of a pulse laser that we had at that time. We started working with it, but it was really gooey and bad and tough to work with. And we had a leak, and it got out the exhaust stack, and the people next door claimed that they might get cancer, so they shut us down. It's popcorn. But anyway, so I had a Spanish student, and I said, let's find another tracer. He did a survey of about 100 possibilities. Many of them were toxic, not good. And some of them had very desirable properties. What are the properties we care about? Well, we need to know the wavelength. We need to know the quantum yield. He came up with acetone, which is, it's something we have in the laboratory anyway. It's a liquid, high vapor pressure, 180 torr. Everybody thought it was fine. And it also absorbed light at a desirable place with our lasers. So that was where we got started on acetone. That was around 1980. Now acetone is used around the world, in many laboratories. 3-pentanone is also a ketone. These are both ketones. The only difference is this has a methyl on the end and this has a ethyl radical. People like 3-pentanone because it has evaporation characteristics similar to gasoline. So you can imagine using this in IC engines in a way that simplifies the analysis. So we're going to talk a bit about flow tracers, acetone, pentanone, IC engines. I've always been interested in trying to do CW PLIF so that we could go at really high speeds. We now have high-speed cameras, but you got to have a high-speed laser, and they can be expensive. So can we possibly do this with a continuous power? And then we got interested in toluene. Toluene is it's an aromatic compound, different chemical structure. It turns out that toluene has some virtues. Extremely temperature sensitive. The virtue of these particular ketones is that they aren't impacted too much by the presence of oxygen. Most flow tracers, if there's any oxygen around, changes their behavior, changes the quench rate. Toluene is one of those. We have to kind of do this without much oxygen around. Okay, this was one of our early results. This was a temperature image using acetone and understanding the temperature dependence of acetone. So this was a flow of air up over a heated rod. We use soldering iron. So basically, turn the soldering iron on this side, flow the acetone-seeded air over, and take a picture. And so this is a little different display. This is a repeating pattern. So this is a pattern which reflects temperature with about 10-degree contours. So this is so good that you can take this image, which is sorted by intensity, and then distribute it over 5-degree intervals. So this blue is not the same as this blue. It's shifted by there's blue repeats itself every so many degrees. This was Mark Thurber, one of my students. Actually, Thurber was a Princeton student. So this was kind of our first time to try to do temperature. Now, how did we get temperature? Well, the mole fraction is fixed. We played the trick. Well, fix the mole fraction and then take advantage of the temperature sensitivity. Okay. If the mole fraction is not fixed, then you have to use ratios, and I'll show you one of those in a second. So But our fluorescence signal now is always photons in, fraction absorbed, fraction emitted, fraction collected. So here's the collection efficiency, here's the quantum yield, that's the fraction that are re-emitted. Here's the photons absorbed. So photons in, photons absorbed depends on the number and the cross-section. So when you go to a big molecule, we don't talk about line strength anymore. We talk about cross-section. It's equivalent. Remember, in the absorbance, or the K nu L, can be written as N sigma L. It's still dimensionless. They're just a different way of expressing the absorption probability. So photons in, photons absorbed, cross-section. The cross-section now depends on the species and function of lambda and T, and the fluorescence quantum yield. So all the physics is kind of like right here. Physics is what you have to understand. The question is, what can we use that would be operable at room temperature? Just a cartoon to show you what we might be interested in, some sort of a jet. So the background was, you can't use oxygen. You'd love to use oxygen or nitrogen. You can't do those. They don't absorb conveniently. Oxygen does absorb in the vacuum ultraviolet, so you actually can't propagate light through the air at shorter than about 190 nanometers. So that's not good. So you'd like to work at a little bit longer than 190, but it turns out that it only works at high temperatures. So we do oxygen emission fluorescence if the temperature is high. Nitrogen we don't do. So we had this biacetyl idea. It was smelly, hard to handle, highly, and it also, this is the structure of biacetyl. There's a methyl, and these two, when you see this double bond to O, that's called a carbonyl group. And so it has the smelly nature, and it's impacted by O2. Around early 90s, Lozano was my Spanish student. He's the one who found acetone. It looks chemically, it's kind of similar, really, methyl, but now you have this carbon here, just down here. So the bonding structure is a little different, and that changes the behavior of this compound. And so the idea was, once we found it, and he evaluated like 100, it looked really good. You need if you can do this at room temperature, you need a liquid which has a high vapor pressure, because that's the number density that you can have. So you want something that has a high vapor pressure, a strong absorption coefficient, and a strong fluorescence yield. That's what you want. So now, when you look at the absorption structure of acetone, and it's about the same for 3-pentanone, here's the absorption feature. So you see there's no discrete transitions anymore. When you have a big molecule like this, it absorbs. Now, is this a electronic transition or a low vibrational transition? Electronic, good. Got an answer. Okay, so we're down into the, this is approximately 4 electron volts. This is electronic transition. And the fluorescence that will be re-emitted is at longer wavelengths. So the trick you play in fluorescence is you absorb here, detect here. So you can have a filter that blocks the scattered light that comes from this laser source. Because remember, this signal is small compared to the signal you send in. You can also do some time gating. So the advantage of these ketones is that they give strong signals, non-resonant fluorescence, meaning the fluorescence is shifted. It's similar enough to hydrocarbon fuels that the combustion and engine people were really interested in this. Now you can use this a lot of different ways. There's the combustion people, but the fluids and heat transfer people were interested in this too. So you see some sort of flow field, maybe it's a jet. You illuminate it with a laser sheet and record at right angles, and you use a CCD camera. Now, once you get out past around, say, 400 nanometers or so, you don't have to have an intensifier. So we could buy in a scientific grade, unintensified CCD camera, which was excellent performance, without the complexities of an intensifier, without the cost, and much bigger dynamic range. So what if you're a fluids person and you're working room temperature, constant pressure, just mixing, this turns out to be really easy. If the temperature is changing, we got to be careful. If it's compressible, you got to be careful. But so in the case where you're doing just room temperature, constant pressure mixing, this is really an amazing concept. but there's still some physics somewhere. Here's the physics. When you have a big molecule like this, an electronic transition, and it's usually, instead of the x2 pi we would have had for OH, it's written as S sub 0, meaning that it's a singlet state. Spin is 0. Ground state is denoted with the subscript 0. The first excited state that's a singlet is written S sub 1. Now, that's just an energy level on top of which there are all sorts of rotational states buried in this molecule. Once you get to this upper state in some family of rotational states, what can happen? You can fluoresce, which is good, that's the signal, and the lifetime for that is about 2 nanoseconds. And the inverse of 2 nanoseconds is the A coefficient. So if that had been 1 nanosecond, that would mean that the A coefficient is 10 to the 9th. That's good. Big A. It's good. The enemy is Q. What is Q? Q can be the collisional quench rate, is called. It goes back down. But remember, I told you that maximum you can have is like 10 to the 9th or 10 to the 10th. So already we're looking good. A is big. What actually happens is that there's something called the transfer rate. It takes you from the singlet manifold to the triplet manifold, which is denoted as T, and this one happens to be called T3. It's actually a little more complicated than that, but this is the simple picture. And so once you're here, it can also come back down. But because the spin has changed, this is quote unquote forbidden. That is a phosphorescence. So phosphorescence is long-lived fluorescence. Fluorescence is short-lived. So this one has the high A coefficient of, say, 10 to the 5 to the 8th. This has a low A coefficient, and it's quenched by O2. So once it's here, it's pretty much out of the picture. We're only going to collect this light. So we're going to turn our camera on and off, and we're only going to collect that light. So a short pulse laser collects some light. We ignore all this stuff. But the enemy is Q transfer. What is Q transfer? The nice thing about acetone is it has a high vapor pressure. It means you can easily produce this and mix it at the volume fraction you want. It's cheap, it's non-toxic, easy to handle. Lifetime is short, independent of oxygen. That's a big factor. It has a constant fluorescence yield. Oh, what does that mean? If you're at room temperature and you do this in oxygen, the fluorescence yield is huge. Approximately 1 in 500 photons is absorbed photons is re-emitted. That's much better than what we saw before, right? It's huge. Each one of these states is kind of a manifold of vibrational nodes. So we get this big molecule, lots of vibrational modes. It's like a sea of quantum states. Question is, what's fluorescence yield? So it's going to be A10. This is the A coming back down. Averaged somehow over all of the different states that were up here. Divided by A plus Q. Well, what's Q? Well, Q turns out to be dominated by this one. So these overlapping energy levels are very efficient. So every time a molecule is kind of vibrating, it's pretty easy for it to somehow transfer over here to the other side. But anyway, that's why it's 0.2%. That's telling you that this Q is 500 times bigger than A. Here's the lifetime, 5 times 10 to the 8th. That's telling you that Q is 500 times bigger, so the order of 10 to the 11th. Higher than the normal collision frequency. It is what it is, but this is still a very good number. So that says that the fluorescence signal is going to be proportional to the number density of acetones times the number of photons you send in. Because, this is probably the important point, I should have underlined this, because the fluorescence yield is a constant. All of a sudden, I don't have to worry about Q. It just is what it is. So if you're at atmospheric conditions, temperature and pressure, many fluid experiments are, the fluorescence yield is a number. Amazing. If it's a number, I can take the fluorescence coming out, and assuming I've illuminated with a uniform sheet, the fluorescence coming out is directly related to the number density of the acetone. And if I'm doing this at constant pressure and temperature, it's immediately the mole fraction. That's the power of this idea. You have to look at the absorption spectrum to decide what laser do I buy. You can buy a laser at 266, quadruple jag laser. You can buy a laser at 308, xenon chloride laser, or you can ROM on shift. So you can get lasers at essentially anywhere in this region. Where do you want to be? You might want to be here. Why? Because you absorb more photons. The fluorescence comes out like this, shifted to longer wavelengths. Now, if you measure the fluorescence intensity, you have to be very careful how you do this. Usually you use some sort of a spectrometer, and then you have to recognize that that spectrometer doesn't have a uniform response, and it's really hard to measure absolute intensities, constant units. An example of somebody who corrected or did not correct their non-uniform performance of their system. So if we excite at 308, which is like right here, I say, well, I want to get all the signal I can, so I'm going to have my detector get all this. Now, you got to be a little careful because your detector's response is not uniform. So what does it mean? So you have to calibrate a little bit. But the good news is the fluorescence is separated from the absorption, so you can filter out the scattered light from the laser. This is what a student named Scott Smith did. He was a fluids guy, working with me and Professor Mungall. Professor Mungall loves jets and crossflow. So here's our jet going into a crossflow. This is all conducted in the open atmosphere in the room. So this is a jet of acetone seated in either air or nitrogen, I can't remember. Crossflow. The crossflow velocity is 5 meters a second. The diameter of the jet was 5 millimeters, and the jet was 100 meters per second. So what are we seeing? This is the signal intensity, which is directly proportional to the mole fraction of the jet fluid at an instant in time, instantaneous image. And because of the high quality, because we have to send in a lot of photons, and the high quantum efficiency, the wide dynamic range of our unintensified camera, the scientific grade camera. Look at it, we can see these really small signals down here compared to the big signal. And we can see the instantaneous structure of these trailing vortices that I don't think anybody had seen these before. How would you see them? A single shot image of this mixture fraction, structure that you see. And of course you can look at this along different lines. This is the distribution along the vertical line. The excitation is 308. This was seated in air. We did this in air. This is the same experiment, but now with the planes in different directions. So here's this horizontal plane. This is what happens if you look at it from that plane, or now looking end on. And this was really intriguing to Professor Mungall. He loved this. He'd never seen this before. And if you looked at this at different times, you'd see it kind of oscillating between heavy on the right and heavy on the left. So he was really into that stuff. So this was really, for the fluids people, finally, we had PLIF in a system that could be used to study fluid mechanics. Or it could have been heat transfer problem, but it was fluid mechanics. Back to this. So there was a conference in Europe at one point, and we were there, and some Germans were there, and some UK people were there. And they all had different conclusions about the behavior of acetone, which led people to realize that why are we getting different answers in different countries? Well, it turns out that we were using different wavelengths of light, and that was a reminder that we had to pay attention to the physics of this problem. Some people were saying that it changes with temperature, and others said it didn't, and it all boils down to this. People hadn't appreciated the fact that the cross-section for absorption depends on the wavelength and the temperature, and so on. So we had to go back and do a lot of physics, and we still do a lot of physics on this. This is the model that my student Mark Thurber developed. I presented this in Germany at a meeting honoring the 100th anniversary of the death of a famous person, was it Heidelberg? Anyway, there was a guy in the audience who asked me this question. He said, that model is physically incorrect. Well, he was a Nobel laureate. He says, chemists don't believe this model, but engineers love this model. This is a model that works, but there's some question about why it works. The Nobel laureate, I didn't know who he was, but I'm sure he was right and I was wrong. But the point is you absorb from some family of lines here and you go up to here. Now you have to worry about the fluorescence comes back out. Well, there's the quench rate, K, and there's the fluorescence that comes back out. But also vibrational relaxation takes place in this manifold. If you're doing this at, if you're pumping something, if you start from what's called the average thermal level, and if you go to a level up here that's not average, then there's going to be some migration of these molecules down towards the thermal average. So it turns out that these intersystem crossing rates and oxygen quenching vary with energy, and that was what we had to build this complicated model to describe this, only because we were working with variable temperature problems. If it hadn't been for that, we'd be okay. So if you go into a compressible flow field, you want to study mixing in a supersonic jet, you have variable pressure and temperature, and you have to build a model. And this model is now in place and is used around the world. You have a similar model for 3-pentanone, but here's what the bottom line. If you look at the relative signal, here's 3-pentanone. So now instead of having methyl right here, you've got this ethyl. If you look at the signal you get, and this is why people were getting a different answer in the UK and in Germany and the United States. If you're using different wavelengths of light, the fluorescence response is different with temperature. And it was obvious after we met at that meeting. This was the problem. So there's reasons to use for different colors. If you want a signal that's kind of independent of temperature out to, say, 700, you use 308. If you want a signal that's very dependent on temperature, you use 248. Well, so it's good and it's bad. It's an opportunity and it's a problem. So this led me to think, well, why don't we use ratios? Why don't we take the ratio of the excite at 248, take the image, excite at 308, take the image, and the ratio is going to be very temperature sensitive and independent of the amount of the material. So this is at 1 nitrogen. So if you take 3-pentanone and you do this at 308, 248, look at the incredible temperature dependence. If you want to measure temperature, wow, you could measure it really accurately. So that's really what we got into for a while. And this was probably Mark Thurber. So we used 2 colors of light, 308 and 266. That's a quadruple YAG laser. Passing it through here, so bang, bang, 2 successive images. And you can either use a single camera, which can be gated down to 1 microsecond apart. But in any case, when you take the ratio, you get the temperature. So here's the instantaneous image of the temperature in this jet from 300 to, comes out at about 700, a heated jet, comes out at 700. But look how it's pretty good. Or we can take the absolute signal and get once you know the temperature, get the mole fraction. So that was the first instantaneous images of combined temperature mixing. We had to put in about 1 to 4%. So a little bit later in time, one of my students was interested in doing this in an IC engine. They use what's called the Bowditch configuration. You can bring in your laser light through some quartz windows, horizontal plane typically. Collect the light, fluorescence light, right angles, then you go down through the cylinder and out under the camera. And so what's going to happen inside the engine is pressure and temperature varying. They're interested in mixing. At this point in time, they're interested in homogeneous charge compression ignition, HCCI. So we developed schemes for doing accurate thermometry, simultaneous T and chi. And then in the case where you use a fixed mole fraction, you can do a single line. So we're back to the same 2 strategies. Fix the mole fraction, measure T, or take the ratio and get both. He used 3-pentanone. There's also a 5-pentanone. And he was able to look at the thermal stratification in this HCCI engine. So temperature uniformity or intentional non-uniformity is the key. And these are images at different times in crank angles. Jordan Snyder works at Pratt & Whitney. So basically, the question is, how uniform is the temperature in a cycle? So at different points in the cycle, the temperature, let's see, so over here, the temperature is uniform, centered around, around here, 450. But at short times, it's cold and hot, so the way that the air is flowing in and out takes time for it to be uniform. In the HCCI concept, you want it to be uniform. So the question is, how do you get it to be uniform? This is a mole fraction of air. He had a strategy for getting the air. So you can see that at this 20-degree crank angle, it's pretty non-uniform. The air coming in here. But by the time you get to, say, 100 degrees, it's uniform. This was really, he was measuring temperature down to, 5 to 7 or 8 degrees with this technique. Mixing was complete after 100 crank angle. They were really interested in using EGR to control the stratification. He went to one-line flip, so if he uses a fixed mole fraction, he can do this. He can do this temperature. This was his very best. So the thing about the one laser is that you're free of the problems that occur when you use two lasers. So he used one laser. Raman shifted, let's see, 300 degrees. But anyway, you could see down here, he's looking for 10-degree variations in temperature across this cylinder. Pretty amazing. So what does this tell you? That there are flow tracers that can be used for temperature and mixture. And you have to be careful if it's a variable temperature flow. You have to understand the photophysics, but it's potentially extremely powerful. And what's the problem with this? Well, it's a hydrocarbon, so if you raise it to a temperature above, say, 1,000 degrees, for more than a couple milliseconds, it burns. So unfortunately, it's not a universal tracer that you could use to test high temperature flows. So there's no really good, the best we found is to use nitric oxide as a flow tracer, but it's toxic. They're really interested in heat transfer effects and whether the heat transfer was responsible for some of these cold spots. Those are the engine people. I became interested in how could we do, on our poor budget, how could we do high-speed imaging? I didn't have a big budget. Well, why not, instead of buying a high burst rate laser that might cost $500,000, why don't we take a CW laser, make it as strong as we can, and had a high-speed camera. So we took our simple frequency double YAG laser, which had a power of about 5 watts. Frequency doubled it down to 266, put it through some lenses. By the time we got over here, we had about 250 milliwatts. Sound like very much. But we're going to do this at low temperature. So we take a nitrogen jet and we use toluene. This is a vertical jet. And we were going to try to do toluene instead of pentanone. The idea, and the reason is because 260, it turns out that toluene has really strong signals. However, we can't do it in air, so you notice it's nitrogen. We asked ourselves the question, how well could we do this? This is Brian Chung, my student. And so as a function of laser power in milliwatts, we asked, well, what sort of percentage fluctuations in the jet could we see depending upon the resolution? So for example, if we wanted to look at 0.4 millimeter by 0.4 millimeter, we wanted to look at 0.4 by 0.4 by 0.4 millimeter, that's pretty small. We could detect about 1% fluctuations with an exposure time of 100 microseconds. So in other words, we could frame at 10 kilohertz and detect 1% change with this system. That's pretty good. Could have been better if we had more power. And so he did experiments like this at 10 kilohertz framing rate with 0.4 millimeter pixels. And there's just some representative results. So he was able to look at fluctuations from image to image. This would be the 10 microsecond exposure time corresponding to 100 kilohertz framing rate, 200 milliwatts of laser power, pretty small. And actually, these were 50 micron pixels, even smaller. So he was able to look at mixing in this jet. I think it's got a lot of potential, but you can't do it in air. You got to do it in nitrogen. We had to use 4% toluene. So this was the poor man's way. Well, if you had a high-speed camera, this is a poor man's way of looking at mixing using PLAF. We could do better if we had used a beam homogenizer and a higher power laser and a better camera. got interested in toluene, and we did some more on toluene. We're back to the same idea. Photons in, photons absorbed, photons converted to photons, and the collection efficiency. Recognizing, okay, someone asked me about surfaces, that we're going to show this, I guess. We did PLIF imaging in a shock tube. And we made a section of our shock tube into a square section. These are usually round. So we had about a 10-foot conversion between round to square. And now down here at the end, here's the end wall of the shock tube. We had windows on 3 sides and on the end wall. And the question was, could we look at the interaction of the reflected shock wave with the sidewall boundary layer and study it, and how close to the surface could we get? So we looked in with horizontal sheets, vertical sheets, lots of issues, mostly trying to find out how close to the surface can we get. And we had to calibrate. So we calibrate first by, here's the end wall. This is a horizontal sheet. Here comes the shock wave. So here's the shock wave right here. So we had, these are weak shock waves. We had 7% of toluene. John Yu, professor in New York. So you can see that we can resolve shock wave structures with this approach. And now this is what we were after. When the shock wave gets to the end wall right here, it goes back. When it goes back, there's this sidewall velocity boundary layer that this wave has to interact with. And this is called the reflected shock bifurcation zone. And so we like to forget it. We like to pretend it's not there. And we do that by using a wide diameter shock tube and say, let's forget the edges. But the fluid people are really interested in this. And there was a theory that these regions had hot spots. And if we were studying ignition, that it might happen here instead of somewhere over here. The plan was to do this at low temperature and then eventually do this at high temperature and see the ignition. We never got there. He graduated and went on. But we were able to get this far. So he could image, and it became a question of, this is 4 centimeters. It became a question of what does the structure look like and how close to the surface could we get? So we do this is called the Lambda shock structure. So you can see no one had ever really seen this. People had used interferometry, line of sight, but not PLIF. This is the first image of the shock bifurcation. And there's some other funny business going on, but you can still see this is what we were after here. No experiment is perfect. There's always a problem. But there were some simulations. Let's see, there's the experiment, and here's I think that's the simulation. Oh, here's the simulation. The program is called Charles. I'm not sure who wrote it. Anyway, there's some good similarity between this side and this side. Some of the turbulence people are really interested in this. We blew it up, and you can see some really interesting structures here that and they're interesting. You do this in a plane because they're not uniform in the transverse direction. You can't use interferometry. We looked at different times, different pictures, structures. So PLIF lets you see flow structures. Make it quantitative is a little tricky because I've swept under the rug. These are intensities. But how do I relate intensity to something like what? Temperature, pressure? These signals depend upon temperature and pressure. So the conversion of these signals to single parameters is not easy. But you can always turn the problem around. If you understand the photophysics, you can ask the computational people to predict the image intensity. We used a lot of toluene after we got interested in this. We started looking at flow fields over wedges at high speed. That got us into the question of how does the best way to do temperature with toluene. So we did temperature with pentanone and ketones. But if we want to do toluene, because of its high temperature sensitivity, we had to go back and study the absorption and the fluorescence spectra. And then we would apply it to some flows like this, a supersonic flow over a wedge. So what we measured the quantum yield as a function of wavelength and saw how it depended upon temperature. So once we saw this, we could decide, well, now the way to do temperature is to take this emission and take this emission with this filter and take the ratio of this to this, and it's going to be temperature. Usually, as you go up in temperature, the spectrum always shifts to the right. always shifts to longer wavelength. Talk with my student. So it's a function of temperature. You have to understand it always boils down to the photophysics. If you do isothermal, isobaric, it's trivial. But if you do a compressible flow field or high temperature flow field, you have to study the photophysics. You do tricks. You know, you evaluate this ratio of these signals that you'd see with your filters to calibrate and get temperature. So we tried different cutoffs in the filters and so on. From this, we could get, basically, the fluorescence ratios became a function of temperature. Fluorescence signal 1 in the red. How well did it work? Here we get 3 demonstrations of this imaging. So we did this at the exit of our expansion tube using this filtering arrangement. And now we go to our standard problem of the wedge and the high-speed flow and the shock angle. And you can see how good this is. Now, this is a problem where once we know this angle, we actually know the temperatures exactly. And now the blue lines are our measurements, and the black line is the calculation. So you can see that it's good, but it's not perfect. We can't measure a couple of degrees. To the cylinder flow, light it again. You can see how well it works. So we use a known flow to see how well you can accomplish your goal of temperature. Be honest about what its limitations are. We went to the jet and crossflow, which is what we were really after. And this is what we really were after. Here's this jet and crossflow, high-speed flow. Here's the shock wave structure. Here's the mixing structure and temperature. This is what we were really after. And this is a way to get at, we wanted to study the mixing of a fuel in a high-speed flow. This is what we were interested in. I think there's a lot of potential for studying complex flow fields with this, but you always have to be wary of the photophysics. Boundary layers, pollutant formation, scramjets, fluid dynamics, plasma-enhanced combustion, all could be attacked with PLAF. A lot of promising tracers, NO for high temperatures, infrared, OH is common, naturally present. Toluene, ketones, NO. There's no really good inert, non-toxic tracer for the, say, 1,000 to 2,000 degree range. That's too bad. These things are limited to about 1,000 degrees. You can do high-speed PLIF. You can do multi-parameter imaging, IR PLIF, a lot of possibilities. Okay, that's the end, essentially the end of my little lecture course. So I took 27 lectures at Stanford and compressed them into 15. So that means we move pretty fast, but you can read these notes, you can buy my book, you can study it some more. And so my philosophy is you need to learn about line positions, line strengths, and light shapes. Now you don't need line shapes for these large tracers, but you do for the small molecules and for quantitative absorption. And the reason for paying attention to this stuff is that there's just no doubt about it. Laser diagnostics will just continue to become routine. Lasers get better and better. More wavelengths, more convenience, more robustness. And you'll be able to buy packaged laser systems so that you, if you want to. I think especially the infrared is powerful because it's economical, robust, cheap. It's a way to get at combustion products. And when you need it, there's a way to make the absorption sensing even better, 100 times better. The people are pursuing these high repetition rate PLIF systems, burst mode systems. That's interesting for flows that have really high speed tracers. People will probably find some better tracers and techniques. I think laser diagnostics will become an increasingly common tool in industry as well as in our university. So, this is my last line. So my other line is, what's new? Over Lambda. Hopefully somebody got that joke. Like if you don't get that joke, we're in trouble. New, what's new? C over Lambda, okay. Oh, I give that joke sometimes to my faculty colleagues. They don't know what I'm talking about. Well, I think the fact is laser diagnostics is great. You have to decide whether you're interested in studying laser diagnostics or you're interested in using laser diagnostics. People in industry usually want to solve a problem. So you have to decide which camp you're in. Are you kind of learning about extending the domain of what laser diagnostics can do, or are you interested in using them? Both types of people. Really expensive laser systems people are fooling around with now, $500,000 or more. Also systems that you can assemble for, $5,000. Imagine them for combustion control. People, they like a system, they just turn it on and leave it there. It could be. So I think for engineers, this is a really good area. If you're an experimentalist and you're interested in this stuff, it's a good area. So we have thermocouples, we got thermocouples, pressure gauges, but we also can have laser diagnostics. So I've tried to take you a long ways. You have to have some appreciation for quantum mechanics. You don't actually have to take a course in quantum mechanics to be comfortable doing these things. Small molecules are easier. Big molecules are a little more difficult. Absorption, there's fluorescence. They both have advantages. There's Raman spectroscopy. I didn't get into that. You could do Raman imaging. It's just the signals are really weak. How to make that better? Questions? Yeah, okay. Sure. Okay, so you can do, if you do line, a lot of people got interested in using line of sights and multiple lines of sight to do tomography. So in principle, for example, if you knew that it's axisymmetric, you could just kind of move your burner across your beam, and you could. So that's a mathematical tool that you can take the same information, apply to mathematics, and get spatial distributions. Then you might say, well, what can I do with Flip? Well, Flip, the virtue of Flip is that it gives you at an instant the spatial distribution. And you can ask, what does it mean? Or you can ask, well, how does it vary in the other direction? So you could do multi-plane Flip, and people are working on it. Some people think, this is popular now, a few people, one of my students, call it volume. You can eliminate the volume and try to do tomography to unfold what's in the volume. I personally don't like this. I personally think, why not you just take it? And when you do tomography, the ultimate spatial resolution is always limited by your number of views. You can't get to millimeter resolution in a 10 centimeter flow unless you're looking over a lot of time and a lot of angles. Because it's math. So why not just take the plane, scan it fast? You get all the resolution in the plane that you want. The only trick is, how do I scan this plane, and do I have a camera that's fast? And so there's some optical engineering here. But I think, personally, that tomography in PLF is not the optimal strategy. I mean, you can do it. If you're interested, why would you do this? You're interested in spatial distributions. Well, if you're going to do PLF, you get the spatial distribution in a plane, you have to interpret it. That's the hard part. You can scan your plane. So to me, the idea of trying to get the spatial distribution horizontally in perpendicular to the plane, I think it's just better to, I would scan the plane. But I know that everybody who's doing this right now is doing things talking about volume and so on. I think the jury's still out on that. But you have to, why would you do this? It's because you need the distribution in the transverse direction. Right. You instantly get it in the plane. But if you need it, for example, you have to ask, what's the out of plane? So you can go 2 planes, you go 3 planes. Sure, you can do that. Thanks. Other questions? Yeah?
So the temperature dependence of the treatment on T-flip signals, is the profile dependent on the pressure?
For the most part, the spectra don't depend on the pressure. It depends more on whether there's oxygen around. So, because oxygen has a different impact on these big hydrocarbons than nitrogen does. So, if there's a flow in which there's variable amounts of oxygen, you at least have to pay attention to this. And that's why we usually, the pentanone, the ketones are less influenced by oxygen. Toluene is highly influenced by oxygen. Of course, that's a problem and an opportunity. Problems are often opportunities. It's just a question of what you want. So you might say, because it's so sensitive to oxygen, I have a trick. I can show that my signal, the change in my signal is because of the oxygen. But if you're, so there's not a good quick answer to that question. But, yeah, the pressure is not as big an enemy as the temperature and the compost and mixture. Other questions?
Oh yeah, that actually sample choice for this. So my actual question would be, what do you think of the future of using laser to detect stream of light to not use the air and force instrument?
Okay. So, you know, in problems where there's soot, people, or particles generally, optical techniques are used to measure the amounts of, say, soot. Typically, that's done by scattering of light, not absorption of light. So you send in some light beam, and the particles scatter light off into different angles. And so you can measure at different angles the light that's scattered from through a flow. And that's how they sort out the number and size of the particles. It's not absorption, it's scattering. You could do, and of course you know that people will do laser-induced incandescence to get at all sorts of numbers. So you intentionally illuminate the soot and get it. And then you look, and then you turn the laser off and you watch the decay of the intensity. And that will tell you something about the size. In the end, you're always limited by, did I have to assume it was spherical? Did I have to assume the index of refraction? It's not spherical, and I don't really know the index of refraction, so soot is really tricky. It's there and it's important, but that's a tough one. People do it, but it's kind of like Cliff. You have to understand the physics to make the best sense of your signals. If you just send some light through and you can see, well, what fraction is, if the particles are in, everything depends upon the ratio of the wavelength of the light, the diameter of the particle, and the index of refraction. Roughly speaking, you can imagine that the fraction of the light that is lost along this direction is due to the blockage of the light by the particles. So roughly speaking, if you lose 10% of the light, that's because of the blockage of the path length of these particles. So it has to do with the size and the number. So quickly you can get close. But when you look at angles, the scattered angles tell you something a little bit more. That's what you have to do. This is the whole subject of light scattering by particles, whole field. So the spectroscopists are over here, and the optical scientists that do particles are over here. It's not really, I wouldn't call it spectroscopy, I'd call it optical light scattering. Van der Waals is the famous book. It's kind of like the spectroscopy. There's the UV spectroscopist, the IR spectroscopist, and each of these fields are so complicated that people live within their little domain. But hopefully you've seen, well, we do the low vibrational and we do low ionic. We at least cover from UV to IR. More questions? Well, our attendance is a little low compared to the other class. I don't know what that says. I hope it's not my lecturing. It's probably, I think less than half of the students are interested in experimental. I think if you want to do experiments, then this should be here. If you need to do combustion theory, I guess you go listen to Professor Leach. Okay, well, if you have any questions, you're welcome to email me. On my book. If you're for Purdue, you can take the course from my student. If you're UCLA, you can take the course from my student. You're the ones who had the energy to take my notes that were 40 years old and finally put it into my phone. So I started, I never took a course in spectroscopy. You know, so you, eventually you just learn, you can learn what you need to learn to move forward in research. And I did take a course in quantum mechanics, actually. I never used it. I think you appreciate quantum mechanics by taking the course. And if you're mathematically inclined, I'm not. Mathematically inclined is beautiful. See how you can derive these results. In practice, many times you can get by with just accepting certain rules. That will faster. So what you're you're interested. Okay, again, I want to thank you for coming, and Professor Law for inviting me again. And I hope that you will all have some interest, continuing interest in nuclear analysis. Okay?